Okay, so I'm going to talk about space junk, and a lot of people on the street have heard about space junk, but it's just misconceptions about, like, what is it? Is it a big deal? Is it any deal at all? And there's the Hollywood version of space junk, which we're going to start with. This is from the movie Gravity, that gives us a really dramatic, gutsy view of space junk and how exciting it is. So we'll start the video. I'm afraid it is, yeah. So. Okay, well, that was pretty exciting, right? So this is the Hollywood version of, of space junk, and as I don't know if you picked up on the conversation, but the idea was that Russia shot down a satellite, and the debris circled around the Earth and smacked into the space shuttle and made a mess out of everything. So that's pretty exciting. in media, you also get the opposite extreme where it's no problem, folks, we got this under control, and you get pictures like this of this cute little robotic garbage truck going around kind of gently, kind of like grabbing satellites and making them go away. So that's kind of the other extreme, and in between, there's all sorts of drawings of different concentrations of junk. Sometimes sometimes it's just like so crowded with junk, you wonder how anything can move up there. So what I'm hoping to do is just kind of give you a bit of perspective on space junk and how much of a headache it is, and what we can do about it if anything needs to be done. So the general layout for the talk is, first of all, is space junk real? Like, is this a real thing or just a bunch of media hype? What me worry, like, is this really something we have to worry about? There'll be some sciencey stuff about orbits and atmospheric physics and stuff, because it has to do with what happens to junk. How much junk is up there? How did it get there? Can we ignore it? What if we do nothing? What's going to happen? Can we prevent more junk from getting up there? And can we clean up the junk that is there? So these are the things I'm gonna talk about. Is space junk for real? Like, has anyone ever seen space junk? Hands up, anyone who's ever seen space junk. Yeah, you've actually should all put your hands up because you have all seen space junk. When you go in the evening and watch satellites flying over, the majority of what you're seeing is actually space junk. It's defunct satellites, old rocket bodies, and stuff. They're not that far away. The lower satellites are just a few hundred kilometers away. And because they're in full sunlight against a dark background, we can actually see them. The satellites aren't very big. Most of the communication satellites are about the size of a human, 2 meters, a couple 100 kilos. And but a lot of that stuff up there is junk, and you've all seen it.
So are you saying that real functioning satellites are too small to see, and what we're seeing is big stuff? Or
no, you're seeing the small stuff. You're seeing the functioning stuff and the dead satellites and the rocket bodies that launch them up there. So you've all seen it. It's up there. The of the kind of registered orbiting bodies, about 60% of what's up there right now is dead machinery, junk. This kind of gives you an idea of how much stuff is up there. This is a panel from the Hubble Space Telescope that was up there for 14 years and brought it back down. And you can see the scale by the person that's just about off screen there. And each one of those marks is the strike of a micrometeorite or a little piece of space junk that hit it. They didn't, the micrometeorites didn't make the holes. The holes were drilled out so that they could look at them under a microscope and figure out what it was that hit them. So it's not quite as dramatic as it looks, but it gives you an idea of the frequency of how often things are hit when they're in orbit. This is a quote from astronaut John Young. Space isn't high, space is fast. The satellites really aren't very far away. They're not very high. We can see them, but they're really fast. And to understand what's the danger of space junk, you have to understand just how fast those things are and how much energy is involved. If you're sitting in a soccer stadium and a sprinter runs the length of the field, it takes about 10 seconds. A Formula One car goes about 10 times as fast and could cross the length of the field in 1 second. The Blackbird plane that I've got listed, that's a big spy plane that's actually faster than a bullet. It could cross the field in 1/10 of a second. But a satellite at orbital speed would do the whole field in about 100th of a second. So if a satellite flew by while you were watching a soccer game, chances are you wouldn't even see it. Like, it wouldn't even register any more than you would see a bullet that was flying through. The last column of numbers here is to try to give a feeling for how much energy things have when they go that fast, because the kinetic energy increases with the square of the velocity, that 1/2 mv squared thing. So if you arbitrarily assign the energy in a sprinter as 1 Ben Johnson unit per kilogram, and compare that with a Formula One car is going 10 times as fast, but it has 100 times as much energy per kilogram as a sprinter. And if you go up another notch to the high-speed plane or bullet, now you've got 10,000 times as much energy per unit mass. You go up to orbital speed, and you're looking at more than 500,000 times as much energy for the mass. So it's just an enormous amount of energy. I have a prop to demonstrate this. So this is a genuine paint flake from my window frame. And underneath here, I have a bullet, a rifle bullet. Now, if you fired that bullet at an astronaut wearing a spacesuit, you can imagine what would happen. It would kind of go in one side and out the other side, and you'd have no more astronaut. Well, this little paint flake at orbital speed has more kinetic energy than the bullet does when it comes out of a gun. So you get hit with, and this is like a fraction of a gram, like 600ths of a gram, but with that 500,000 times effect of the high speed, you do a huge amount of damage with the tiniest little fragment that hits things. And a paint fleck is a good example of that, because every spacecraft is painted for temperature control. And as they get old, things get old and paint flakes off. So you've got, as well as the big things that you can see go by, you've got zillions of little things like this that have broken off or flaked off or fragments when other things hit them. So we're looking at huge speeds and huge energies. This is a chunk of test metal. It's a slab of aluminum, 6 inches thick. And just by comparison, the space station's hull is 2 inches thick. The arrow indicates it on the other side. And that little aluminum ball was shot at this plate at orbital speed. And you can see the huge divot that it made. Obviously, the ball was obliterated. So if that little bit of aluminum that was smaller than a marble had hit the space station, it would have blown a hole through the pressure hull, which would let the air out. But the astronauts inside would all be dead, because you see that flake of metal that's flaking off the inside. It would have just sprayed the inside of the space station with shrapnel. So even something as small as a nut or a bolt can do a huge amount of damage to a spacecraft. We have an actual collision to study. It was in 2009, an Iridium satellite collided with a piece of junk. It was a Soviet military satellite that was past its service life, and they collided up over the Arctic. So this is a diagram of the collision. So this is the Iridium communication satellite, and this is the path of the Cosmos satellite, and they collided up in the Arctic. And so the two of them put together weighed about as much as a Ford pickup truck. And all these little dots are tracked fragments of the collision. And to track them from Earth, they have to be as big as a baseball. So there's about 3,000 baseball-sized metal fragments from this collision. And this distribution, this is what happened within one orbit. One orbit is 90 minutes. So this is how much they spread out and went around the Earth, and then they come back and collide again. And they keep going bang, bang, bang as their orbits cross.
What's the, do you know what the rough elevation is? How far are they up?
Hundreds of kilometers.
Hundreds.
So it'd be like 300 or 400.
Okay.
And then 2 years later, this is the distribution of those fragments. they're color coded for which satellite they came from. Basically, they have completely spread themselves uniformly around the world in low Earth orbit.
Question, how do spaceships, how do things go into orbit without getting hit with them?
Well, the thing about space is that there's a lot of it, right? And you're up there long enough, you're going to get hit by something. And I've got some graphs about that later. There's a thing called the Kessler syndrome, which was originally described by Dr. Kessler. It's a cascading reaction of orbital collisions, which create a cloud of high-speed debris, which makes space uninhabitable for humans or machines. And the idea is that if you have a collision like that, you start with two satellites, and they go smack and they turn into like thousands of particles. And when they hit things, those become thousands of particles. So it's exactly like a nuclear chain reaction. You get more and more and more until you get to the point where there's the debris cloud is so dense that you just can't be there without, like you say, getting smacked with something. And so the mathematicians that look at this have the question like, well, how much junk do you need to have up there before this is inevitable? Because if all you have is just two spacecraft and nothing else up there, if you leave it long enough, like for a million years, eventually they're going to bump into each other. And if you've got 100 satellites, something's going to bump into something a lot faster. So the more satellites you have up there, the sooner you're going to get this chain reaction starting. And some mathematicians say we have already reached that point. There is enough mass up there because there are millions of kilograms of machinery that we've put up into low Earth orbit. It's inevitable that at some point in the future, this number is going to skyrocket. And so this particular calculation model along here is time. So this is the present. This is in 1 century, 2 centuries. This is the probability of any given satellite being made non-operational. And the probability goes from just about 0, which it is now. You can put a satellite up there and it's not going to suddenly blow up. But the probability increases to 1, which means absolute certainty. So if you go far enough in the future, and you can argue about whether the curve is like this or like this or like this, but if you go far enough in the future, you get to a point where it's absolutely certain that low Earth orbit would be uninhabitable. You can't have space stations or space capsules or communication satellites or anything up there because it's going to get smucked. So this is the big worry, is this Kessler syndrome. And some astronomers think that we have already reached that inevitability. So even if we do absolutely nothing, don't send anything else up there, don't do anything, we're going to end up on that hockey stick curve and lose the use of space. So I just give some just very basic stuff about orbit, so you understand the rest of the talk here. So here we have kind of like typical orbits. We got a low one, the yellow one, got a high one, the blue one, and then here's an elliptical orbit that kind of connects the two, and that can be used as a transfer orbit. The arrows show the velocity at that particular point in the orbit. So a low orbit, the object is going faster than a high orbit, and in an elliptical orbit, when it's close to the Earth, the near point, it's going faster than when it's at a high point. So suppose there's a piece of junk up here that we want to get rid of. We want to send our automated robotic garbage truck up there to get it. So we launch our garbage truck satellite into this low orbit, and now we have to get it to rendezvous with the piece of junk. And to do that, we have to speed up. We have to increase the speed so that we can transfer into this elliptical orbit to get up there. And once we get up there, we've slowed down because we've been going uphill. So we have to burn the rocket again to go fast enough to match the speed so that we're going along in the same direction at the same time and the same speed, you can latch onto it. And then if you do latch onto it, you want to bring it back down, then you have to use your rocket again to slow down. And when you get down to a lower orbit, you have to do more braking because you picked up speed coming down. And each one of these stages, you're burning propellant. And that's the cost of trying to get to junk to do the rendezvous thing, is the propellant cost. And it takes fuel no matter what you do. If you go up or down, you're burning fuel. And you have to get that fuel up into orbit. And there's about a 10-to-1 ratio between how much fuel you burn in launch versus the weight of what you get up into space. So to get a kilogram of fuel up to this point to start the exercise, you have to burn 10 kilograms of fuel to lift it up there. So this is a very fuel intensive thing. And even if you do all this and go up and grab something and bring it down, you want to go for another one, you got to burn more fuel, and you had to carry that fuel the whole time because there's nowhere to get it. There's no gas stations up there. So logistically, it's a very difficult thing to match orbits and grab onto things. So when you see drawings of little robotic things with arms grabbing garbage and thinking like, oh, wow, yeah, that's done. You know, he's grabbed the garbage, for ready to go. That's only part of the picture. The other part of the difficulty in doing the rendezvous and grabbing the garbage is you have to match orbital inclination. So in the previous drawings, the orbits were all in the same plane, but in reality, they're not. They can be in any inclination in relation to the Earth. So say that the yellow orbit is our garbage truck, and the blue orbit is the piece of garbage it's trying to rendezvous with. Well, even if they arrive at the same place at the same time, they're not going in the same direction. And you have to burn to make this vector turn into that vector. And that takes a lot of fuel. And in fact, the more inclined it is, the more fuel you have to burn. And if there's a big difference in inclination, it rapidly gets to the point where it's just not worth it. You burn less fuel by starting all over again from sea level and launching another rocket. So the rules you get from that is it takes fuel to go up or down, and it takes fuel to change orbital inclination. So it just takes a lot of fuel to move around and rendezvous.
You ever seen that?
Rendezvous or collect garbage?
Yeah, quite garbage.
No, there's been some experiments. I've got some pictures later where they've tried out ways of grappling garbage, but nobody has actually sent a garbage truck to get a piece of garbage yet. The other thing about orbits is that they come in different sizes, and there's basically 3 kinds of orbits up there for satellites: low, middle, and high. Low Earth orbits, that's the space station and all the Elon Musk satellites, big swarm of them right around the Earth. There's the high orbits, the geosynchronous orbits, and that's for communication satellites. So if you see anybody with a fixed satellite dish on the outside of their house, it's looking at one of these geosynchronous satellites. And they have the novel property that they go around once every 24 hours in the same direction as the Earth. So they're kind of in effect hovering over exactly the same place on the equator all the time. So it makes it really easy because you don't have to track them because they're not moving relative to the surface of the Earth. So this is very crowded real estate here. There's virtually no slots for more satellites up there. And the middle Earth orbits are where the GPS satellites are. So to give you an idea of how crowded it is up there of future junk. So this is a collection of tracked, registered satellites. You can see that what looks like a ball of yarn here is hundreds and hundreds of low Earth orbiting satellites. And the ring here that looks like Saturn's ring is those geosynchronous satellites. The green line is where the geosynchronous satellites would want to be. You can see that there's a whole bunch of blue orbits that seem to be kind of like tilted out of kilter. That's junk. those are old satellites that can no longer maintain their position. And they drift that way because the moon and the sun tug on them. So this is really valuable real estate, and there's a lot of junk that's crossing it as it does its kind of oblique orbit. And then the GPS satellites are kind of in between. But all those things, eventually they run out of fuel, or bits break and they turn into junk. It's often fuel limited because satellites won't maintain their, you don't want them tumbling. They have to maintain their orientation with the stars. That takes fuel. And they have to maintain their orbit so they don't get pulled off by the moon's pull, like what happened to all those blue orbits. So they need fuel to stay in position and function. And once they run out of their fuel after, say 5 years or something, then they become junk because they can't do their job anymore. So this is kind of like a compressed life history of an individual low Earth satellite. So they get launched, they work, run out of fuel, and then they're dead, they're junk, and then they slowly lose altitude because of air drag. Even though there's very little air in space, there is some. So eventually they fall down and burn up and deorbit. So in the launch phase, these little blue arches, those are the boosters. There's usually several stages that get dropped off, and they don't go up into space, they fall back down and splash and burn up. But there's always a launch vehicle that arrives up in orbit because it has to go up there to put the satellite up there, and now it's in orbit. It's just like your cars are all in the parking lot because they brought you here. Where else would they be? They have to be there. So for every satellite, there's a booster, and the boosters are much bigger than the satellites. So they're like thousands of kilograms, and the satellite might be hundreds. But they just keep on orbiting for the entire time that the satellite's up there. So typically the satellite will get thrown up there, it'll do thousands of orbits at a few hundred miles, and then it'll run out of poop and shut down, but continue as junk for roughly 25 years. 25 years is kind of a magic number in this business, and I'll explain that later, why it's kind of like a key time frame. I could talk about atmosphere because it's the atmosphere that slows down those low Earth orbits, so that the satellites deorbit. I just love this picture. This is taken from Apollo 12, and this is the sun coming up over it's basically dawn, the first little glimmer of light coming over, and this curve is the Earth. So you can just imagine, how big the Earth is and how thin the atmosphere is. So that what we think of the atmosphere in terms of stuff that we can breathe is extremely thin, but that it never ends. It just becomes more and more tenuous as you go up. And this is the same photograph turned on its side with a few little additions to give you a sense of scale. So this big black blob over there is the Earth. You can see its curvature. This little triangle represents Mount Everest from sea level up to the peak. The top of the light blue is the altitude that airplanes fly at, commercial airplanes. And this is the space station, obviously much larger than it would be in real life, but that's the altitude is in the correct scale. And this yellow line is a completely arbitrary borderline of space called the Kármán line at 100 kilometers. And it's completely arbitrary. It's just like, that's how high you have to go to get a little astronaut pin on your lapel. So the air just gets more and more rarefied as you go up, but it doesn't end. Like the space shuttle is going at umpteen thousand miles an hour through very thin air that slows it down. And if you don't keep boosting it back up again, it'll come down on its own, and it will in a few years. So every so many months, they give it a little boost and turn on the rocket engines and push it back up again. This is the same as the previous slide, except it gives you the larger scale with the geosynchronous satellites and the GPS satellites. So This is correct scale in terms of the diameter of the Earth and the distance. These numbers down here indicate how long it would take for the air to slow down the satellite to the point where it would spontaneously deorbit. So the low Earth orbits where most of the satellites are, you're looking at 25 to 250 years that they'll slowly just spiral down and then go splat. When you get up to GPS altitude, it's thousands of years, like 10,000 years before they would just spontaneously fall. And up at geosynchronous, it's millions, like hundreds of millions of years before they would fall down. So these guys aren't dropping on our heads anytime soon, but the low Earth orbit stuff does come down. So how much junk is up there? This graph shows number of kind of registered tracked objects like satellites and old space stations and stuff like that. This is a timeline, so this is back in Apollo times during the moon landings, and this is now. And there's separate lines for rocket bodies and non-operational payloads, which is a polite name for junk. And then this is the total number of big heavy things up there. And you're looking at thousands, like 5,000 objects that are big and heavy, like, you know, car-sized things up there. The total mass of all this stuff, and this isn't all the little stuff, this is the stuff that's big enough to be registered as an object. Total mass, 2 million kilograms. That's how much stuff we put up there since Apollo days. And that's the equivalent of 11 747s. So if you line up 11 747s, cut them into pieces and throw them up into space, that's what we put up there. What's still up there? And so where is this junk? What's the most crowded with junk? So once again, these are mark the years to spontaneous deorbiting. So this is the middle Earth orbit. This low Earth orbit and middle Earth orbit and geosynchronous. And you can see most of the most crowded part of space is the low Earth orbit. And because that's where we put most of the satellites. Once you get up to GPS altitude, there's really not that many particles up there to run into. And then when you get up to geosynchronous orbit, there's a peak because of that crowded real estate ring there. So the strategy for dealing with that depends on the, I don't want to go that way, try that way. It depends on the height. So this is kind of the 25-year limit. There's international organizations and spacefaring countries have got together and kind of promised that they won't let stuff stay in space for more than 25 years after it's lived out its service life. And any orbit from here down will spontaneously deorbit itself because of air drag. So stuff 25, the kind of 25-year height, few hundred kilometers, isn't the worry it's going to fall out. So for instance, Elon Musk's satellites, the Starlink, they just lower them down to this kind of altitude at the end of their life, and then they fall down. The majority of the junk is up at a point where if it's going to fall out of the sky within 25 years, you have to do something active to get it down to the height where it'll fall out of the sky. And we'll talk about active deorbiting and how that can be done. Once you get up to GPS height and above, it's just not practical to actively deorbit things because they're so high, and you have to get your garbage truck way the heck up there, and it's so far down that you need a great big rocket boost to slow them down enough to get them down to the atmosphere. So up in this altitude, they take a graveyard approach where they identify orbits where there isn't anything useful and say, put your satellite there where it won't bother anyone. So for the geosynchronous satellites, what they do is they boost them up higher. This graph will kind of go like way down like that because there's nothing useful up here. So they boost them up another 1,000 kilometers and leave them there. The GPS satellites, there's kind of military issues, and they're not really very forthcoming with what's going on there, but it's valuable real estate too, so the military are kind of concerned about what's going on there. So what do we do about all that junk? That saying about what do you do when you when you dig yourself in a hole? Well, the first thing you do is you stop digging. And that's the first thing we should do is don't make more junk, because it's going to have to be dealt with at some time. One way of doing that is by passivating spacecraft when they've reached the end of their service life. And passivating basically means disarming them so they don't spontaneously blow up. So it means releasing all the pressure from all the tanks. There's often compressed gas or propellants and stuff. So let that all hiss away so fittings won't blow and stuff. Disconnect the batteries from the solar panels. The batteries will discharge spontaneously, and if they're not hooked up to the solar panels, they can't get charged again. So there won't be any electrical things happening. And so this passivating is something that's agreed to in the treaties, but you have to plan that ahead of time, because you have to have a mechanism in the spacecraft to do that, to release pressure and disconnect solar panels and stuff. The other part of these international agreements are to reduce the altitude to the point where it's 25 years before self-deorbiting. And you can do that by increasing the drag. You can like release like parachute. They've got like big sails and parachutes that make them less ballistically efficient, so they drop down faster. You can do a deorbit burn with the motor if you have a rocket engine that's capable of doing that, and you've saved fuel to do that. But remember, most satellites, the end of their service life is when they run out of fuel. So if you're if you say, well, you got to save fuel for the deorbit, that means you're reducing the service life of the satellite, which isn't going to be popular with the people that paid to put it up there. That your satellite's only going to work for 4 years instead of 5, just so you can throw it away early. There's something really interesting called an electrodynamic tether, which uses the Earth's magnetic field to slow the satellite down. And what they do is they have a spool of wire and let it out, like kilometers of wire. And because of tidal forces, the wire will extend up radially from the Earth in a straight line and be held under tension. And so this wire is sweeping through the Earth's magnetic field. And if you then put an electric current through it from your solar panels, you have an electric current moving through a magnetic field, which is by definition an electric motor. And you can, with this technique, you can either speed up or slow down a satellite. But of course, it has to be planned ahead of time, and you have to have that equipment on board, and it costs money and adds weight. The last one there, this precision deorbiting. Most of the deorbiting is non-precision. It's just get it down and let it burn up. The trouble is that some spacecraft don't burn up completely because they've got big solid metal pieces in them, like rocket motors and compressed gas tanks and stuff. And because they have parts that will survive to impact, you have to choose where they impact. And that means in the South Pacific between Chile and New Zealand, that's like where they're going to drop the space station when it comes down. And that requires a lot of fuel because you have to have a very steep descent, so you've got control over where it hits. So that's an expensive way of doing it.
So basically, you're just taking the junk out of space and putting it into the ocean.
Yeah, or burning it up and letting it be in the atmosphere, which some people are concerned about too, because there's some nasty chemicals in there. Some of the rocket fuels aren't very nice, and the metals for the batteries become gaseous and stuff. And so there are people that worry about it. It's somewhere. So those are the don't make more junk approaches. And then there's the get rid of existing junk approach. And one of the popular things in the media is laser ablation, where you shoot the damn thing. And so you get like a great big laser, either ground-based or space-based. And as the satellite's coming towards you, you blast it with the laser and vaporize material from the front surface, which then acts as a rocket because it's like spraying off gas. and that slows it down and it drops. The trouble with this is, this sounds an awful lot like an anti-satellite weapon, because that is exactly what it is. And there's a lot of political implications for countries developing ways of shooting down satellites. So this idea, you know, is good for science fiction, but not good around the bargaining table. The last way is kind of the garbage truck approach, where you actually go up there with your garbage truck and you grapple. I love that word. That's the word they use for grabbing things. You grapple the garbage and grab it, and then do something with it, like attach a parachute to it, or put a rocket on it, or carry it down or something. Grappling stuff is like a real big technical challenge, because first of all, you have the rendezvous problem of matching orbits and speeds and direction and all that, which requires a lot of fuel. And then what do you do when you actually get up next to this thing? Because this might be like a spent rocket stage that weighs like 10,000 kilos, and it's going to be tumbling. The spacecraft don't tumble normally because you don't want them to. They're not functional if they're going ass over tea kettle. But if they're dead, they pick up angular momentum, either from light pressure or hitting things or gases venting. And if you have an inert, non-functional spacecraft that's been up there for years unattended, the chance of it having absolutely zero angular momentum is absolutely zero. It's going to be spinning in some direction. So you got something that's the size of an F-350 and the weight of one, and spinning. And how close do you want to get to this thing? Because if it comes around and clonks you on the back of the head, or your garbage truck, you can do serious damage. So trying to come up, snuggle up against a tumbling, derelict, uncooperative satellite is a really challenging thing to do. And even if you get close to it, how do you attach anything to it? Because you can't use magnets, because they don't use ferrous metals in satellites. Adhesives don't work in vacuums because all the solvents evaporate. There aren't grapple points, because where would they put them? They don't know how it's going to be spinning and where it's going to want to be grabbed. And if you just try to grab something that goes by like a solar panel, you'll just like tear it off. Now you got more fragments spinning around. So it's a real talent, or a real challenge, even if you can get up next to it. And here are some of the methods that have been tried. There's been the European Space Agency did this. So they sent up a satellite to grab another satellite. So they had one method they had was a net where they fired it. These are little weights on the end of the net that went boom, and to kind of like catch it. What you do if you get a net around it is kind of another issue, because it's still going to be tumbling, and now you've got it on the end of a leash. You kind of got a tiger by the tail, and you still got to stop it from spinning. This is one of these parachute type things. So this was deployed from a satellite. So the satellite was equipped with it before it went up, and the idea is that it adds drag and drops out. This is a harpoon. So this little test satellite had a boom that extended out with the target. It's basically kind of like taking a selfie, and then it went and shot the harpoon at it. It didn't work really well. And once again, even if it does work, what did you shoot it into? Like, did you shoot it into a propellant tank? Do you really want to do that? And then you got it on the end of the wire, and you got to deal with it. And then this is the kind of grabby approach, which apparently is going to be tried in 2 years. NASA's going to send something up with it to take the grabbing approach. But it's a difficult thing, and then you still got to get it out of orbit. So it's not easy, even if you can get up there. It's not easy to deal with it once you're right up next to it. And then there's the politics of space junk. And you think, like, wait, how can that be political? Well, it is. I don't know if you're familiar with the tragedy of the commons. This is a common issue with economists. there was a paper that was written on the fate of the English commons. Every village would have the commons where they would, you know, it's just an open grassy area where they would have visiting fairs, and anyone could do anything. They could shoot rabbits, or they could, you know, graze their horses in there. And the trouble with the commons was that they were always wrecked because everyone took advantage of them. So if anyone can graze their cows there, well, then I'm going to, and hey, now I can get 3 more cows and graze them on public land and get the milk. And as a result, the commons get degraded to the point where they're not worth anything. And the basic message from it is that anything that's a common good that everyone has access to, if people act in their rational self-interest, it produces an irrational, unproductive result. And that's what's happened with CO2 in the atmosphere. It was a common good, and we all took advantage of it by dumping our CO2 in there because it suits us. You know, it's the cheapest way to get energy, and we've gone and ruined it. The same with fishing. You know, if you don't control it, it's in everybody's interest to fish as much as possible, otherwise the next guy will get it. And that's what we've done with space. We have abused it. And the result is that we can potentially make it through the Kessler syndrome. We can make it useless. So there's that aspect, and the only way around it is politics. Like, people have to get together around a table and agree what to do, limit their own self-interest for everybody's interest. Another part of the politics is the anti-junk technology, is anti-satellite technology, whatever it is. Because if you can take down junk, you can take down your opponent's satellites. Another problem is junk monitoring secrecy. There's a whole bunch of databases that different governments have about what's flying around up there, and they track them with radar and telescopes. But they're a little cagey about letting out that information because it has strategic value. And, you know, they're kind of, you know, they're not going to tell you the whole story. They'll tell you part of it. So everybody's got part of the story. Another problem is ownership. Under space law, an object in space remains the property of whoever put it up there. So what's one person's junk may not be junk to the owner. They might have other ideas, like they might have deactivated a satellite knowing that it has useful life, and they're just keeping it as a spare in case they need it in times of war or something. Somebody else calls that junk and wants to take it down. They're going to get kind of exercised, but they don't want to let it out that that's what they're doing. And of course, there's the cost sharing thing. You know, the countries that put out the most junk, in theory, should be responsible for cleaning up their junk. But tell that to people that release CO2. So what do we do? Well, there's a few things we can do. We can, you know, encourage this immediate deorbit for all spent upper stages. So if an upper stage gets a satellite up into orbit, if everyone can agree that it saves enough fuel to deorbit itself right now, then it's not going around for 25 years, and it reduces the chance that it's going to bump into something else. So that's a useful feature in an international treaty. Continue the 25-year deorbit rule for low Earth or payloads, and most spacefaring nations have agreed to do that. There's still some outliers like North Korea and Iran that don't play well with others. There's a proposed policy, is the one up, one down policy for higher orbits, and that's every time you put one up as part of the same mission, you have to bring a piece of junk down the same weight. And so you can choose what junk it is, but it has to be roughly the same weight. And this is a reasonable thing to do, because if you're allowed to choose which piece of junk, then you can design your delivery launch vehicle to accommodate that particular piece of junk. For instance, there's a way of grappling rockets. Every rocket has a bell sticking out the back. And there's grabbers that are basically a stinger that goes up the center of the bell and grabs onto it. It's because the rocket nozzle goes in and then opens up into a combustion chamber. So it's a relatively easy thing to make a generic rocket gooser. to go up there and grab it by the combustion chamber. And because the rocket has to be along the center line, it's lined up with the center of gravity of whatever it is that you're grabbing. So if you do a burn your rocket, you know you're pushing straight into the center of gravity. You're not going to send it up spinning off. So that's a policy that you know that they're trying to promote, and put work into the all the technical problems around rendezvousing, grappling, and deorbiting technologies. But it makes sense to concentrate on the highest risk satellites, because you don't want to remove low risk junk when there's high risk junk that would be better to spend your efforts on. So there was a group in Japan that looked at all that junk up there, and they said, what are the most important things to get rid of in terms of the Kessler syndrome? What if we can only remove 100 things, what would those 100 things be to get the best benefit in terms of reducing junk? And what they found was that the real problem satellites tend to cluster. And so this axis is orbital inclination, how much it's tilted from the equator. And this is altitude. And you can see that it's kind of convenient here that there's 3 inclination groups. And within there, here's a really tight cluster at a certain altitude. And even these ones cluster at altitude. So if you send the mission, the garbage truck mission up here, you don't have to do all that maneuvering. You don't have to change orbital diameters and inclination, because they're all clustered about the same. You just have to move a little further along the orbit. You can get another one. So this is kind of a reasonable game plan. Like if we can develop the technology to remove just these 50 top things, then that would probably prevent the Kessler syndrome from ever happening, or at least push it like 500 years or a millennium into the future and kick the can down the road. But it's a big problem. Like for instance, this Envisat, which is one of these ones here, that's a European environmental satellite, and that weighs 8,000 kilograms. That's a big chunk to deal with, and it's going to be like a major mission to get that thing down and not drop it on somebody's cow. There was a cow in Cuba that was killed by a satellite falling on it. Apparently, Cubans claim. So anyway, that's the end of the talk. So I'd leave you with this beautiful picture of the future, where this elegant little robot goes in gently, grabs satellites as they retire and gives them a decent burial. So hopefully we can do that and avoid Kessler syndromes and dead cows. So any questions?
Can you see the video?
Sorry? Oh, right.
How many pieces a year are coming down, do you think? Burning up in the atmosphere right now? Satellite, fired satellite.
It's around 1 a day, something like that, or 1 or 2 a day, something like that.
Do you know if there's an app that predicts when and where you can see them? Maybe first?
Oh, it's actually difficult because they come in at a very, very shallow angle. And if your calculations are off just by a little bit, that can mean like 8,000 miles in terms of where they actually look like a meteor. Yeah, that's right. The steep ones, the targeted deorbits, they're very accurate and predictable, and you know they come down within like 10 or 20 miles of their target. Actually, when they were bringing the Apollo capsules home, that's what they did. They were deliberately deorbiting them for re-entry, and they actually got so accurate with it that they were worried about hitting the ship, and they actually developed a policy of not aiming for the recovery ship, to deliberately miss it by 10 miles so that they wouldn't be really embarrassing. It came down on the deck of an aircraft carrier, and one time it came down within a fraction of a mile of the recovery ship. Yeah, just being too good for your own good. So this is the collision of the of the Iridium and
Okay, so-
Cosmos satellite. It doesn't really add information, it's just a pretty thing to look at. So here's the Iridium network, and here's this innocent satellite, still functional, doing its job, and oops, look what's coming, it's that nasty Russian piece of junk. Boom,
Didn't the Chinese deliberately blow up?
Yeah.
everybody has,
Idiots.
More junk.
so this is the clouds of junk on their first half orbit as they go around. And you see how much they've already spread out, that's only a half an orbit, that's like 45 minutes, and they're already spread out that much. Here they come for a second pass. And the green stuff is all the other tracked objects that were up there at the time. And this is 2009, so there's a lot more junk up there now than there was at that time.
So does North America, the European Union or anything like that have any standards now if it's any satellite up, you have to comply with, you know, plane rules or deorbiting rules or anything like that?
Yeah, they've got the passivation and the 25-year deorbiting. That's for low Earth orbit stuff. I'm not sure what they do with the higher orbit.
So all the Leon Musk satellites, they're gonna have to comply with that.
Yeah,
and
and
your rule or.
they do, because they've got really good propulsion systems. And the plan is to
If you're gonna have audience participation, you have to speak into the mic, there are those people on.
so I'll
Well, it's pretty
So
good, since it's, as long as it's pointing that way. it should
Okay.
be all right.
What was the question, Neil? Did, well, I think it was something about the European Union or the USA sort of have, some regulations about new satellites.
Yeah, the current treaties that virtually all the spacefaring nations have signed, you know, there's countries like India that really has a large space program. And they've all agreed on the 25-year rule for the for low Earth orbit stuff and the passivation. I'm not sure about all the details of the treaties, but oh, and part of that is the graveyard orbit thing for geosynchronous satellites.
Okay, so all the astronomers, of course, are up in arms about all these satellites Leon Musk is putting up there.
Right.
Is there justified concern for that?
For which concern that it spoils observations or that it's a danger?
I don't know exactly what the concern is. I know light pollution's one, but you can't see them anyhow after so many days, I don't think.
Yeah, they're launched in a fairly low orbit and then they make their own way up. I think when those necklaces that you see are, I think there's something like 250 kilometers, and then once they've dispersed, then they climb up to, I think, about 400 kilometers. And then when they finish their service life, they reserve enough fuel that they can get back down to an altitude where the orbit deteriorates.
And what's the chance of, does that increase the risk of collision?
Well, just the
satellites up?
Yeah, just the sheer number, like thousands of satellites, will definitely increase the risk. But they do take evasive action because there are tracking agencies that predict collisions or near collisions, and then the owners of the satellite, if they have maneuvering capability, can avoid it. But the Iridium Cosmos collision that we just watched, that was predicted as a close approach, like a half a kilometer, and they were wrong. They hit. And the dodging and weaving to avoid collision uses up propellant, so it shortens the service life of the satellites. the International Space Station regularly does that. And that's a big heavy thing to move to. It takes a lot of propellant to push that around, but they dodge stuff as they go around.
It's interesting. I put a 4mm lens on my planetary camera and pointed it at the sky. And I was taking it 10 frames a second. And then when I speeded it up, I saw all these things buzzing, or it sounded like bees, or I assumed they were Elon Musk, but actually from what you say now, probably what I was actually looking at was space junk. Because it was really noticeable that you could see sort of kind of all this stuff just buzzing around.
Yeah. Well, there's about 5,000 kind of cataloged objects, and I think when Elon has his sandbox full of satellites up there, that's going to be another 4,000.
Yeah.
So it kind of close to doubles the number of things up there. So it just makes it that
But
much more likely.
I thought it was all this stuff, and then you could really see it.
So what's this? Okay, the question is, what's the service life of the satellites that Elon Musk is putting up?
I believe it's about 4 or 5 years.
I'm going to recommend people use a sky hook instead of a rocket to get up there, and just climbs up the sky hook, pulls down the satellite that's at the other end.
Space elevator.
Yeah, the space elevator.
Take it halfway up and throw it out the elevator.
There you go. Right. Yeah.
Space fishing.
Question? Sorry?
Okay, so what orbit is Leon's car in? Elon's car, sorry.
Yeah, it's in a heliocentric orbit. It's an orbit around the sun. It's not an orbit around the Earth. If I remember correctly, it was kind of like a real kind of like macho thing, you know, single rocket heliocentric orbit, because usually when they send scientific loads up, they do some complicated gravitational slingshot, you know, go to Venus, go to Mars, come back to Earth, and go to Jupiter and stuff, you know, kind of limping along looking for a free ride from gravity fields. But Elon, boom, yeah, straight into heliocentric orbit.
Well, you know, with that much crap up there, we had a speaker here some years back and his wife, and he was part of the Space Wheel project, where they planned areas where there'd be hotels and industrial areas and everything. Well, wouldn't that be in jeopardy if, with all that crap up there, that idea wouldn't really work, would it, with the stuff that's there now?
That would certainly be a concern. Yeah, the bigger the thing you got up there, the more likely it is to be hit by something.
It's too bad they couldn't put up one big thing. Each country has a little section they can put their little electronic whatever's in it, and not allow any stuff in space. They have to use that as a base.
Oh, that would be
That would
interesting.
nice.
Tree out.
It'd be a lot environmentally better.
Just unplug the Randy.
Any other questions?
Bruce, it says that there's no anti-proliferation measures, eh? Elon's thrown up there in that place. They're just putting these measures on how to deal with them, but they don't seem to be alarmed at the number that's going up, do they?
So the comment is, it doesn't seem to be any anti-proliferation agreement or a treaty or whatever.
The commercial satellite launchers have to get permission to launch stuff. So they have to, you know, submit plans and get approval from, if you're an American corporation, from the American government. And I assume that part of that approval process is compliance with existing international treaties for mitigating garbage. And when Elon has been asked about all the garbage he's throwing up there, he says, well, it'll all come down. We're managing it. We've got plans to bring it back down. So. And we believe him, right?
Show some payment for, you know, his application to approve the satellite.
Yes.
But still, I mean, it does come down and it does have an effect on wherever it lands if it doesn't burn out.
Yeah, well, they do burn up, and the designers of satellites design them to burn up. They don't want big chunks coming down, and they often design them so that they come apart, and they calculate how long, at what altitude different pieces are going to burn up. And there's actually a move to start using wood in the structural bus of satellites. And I mean, it sounds wacky, but it's not, because wood is actually a fabulous material. It's very rigid for its weight. It's transparent to radio waves and radar. It's non-conductive, and it burns at a very specific temperature. They know exactly what altitude that's going to burn up. And if it's a structural element, then it burns, and then the satellite fragments, and the fragments are small and they burn even faster. So Norway is big surprise there is is really into this, and it's not a log cabin design, but Norway's is designing wooden frame satellites, and Japan is, I think, going to fly one within the next year. First wooden satellite. Yeah, that's right. Sky high.
They need a prize for the first person to launch a rocket into space that's made of wood.
Yeah, that'd be tricky. But it actually is a fabulous material. If most structures aren't designed for strength, they're designed for rigidity. And that's like boats, airplanes, cars, all this. Like that's the reason that cars are made out of steel and not aluminum. I mean, everyone knows, oh, aluminum is lighter than steel. Well, a pound of aluminum isn't lighter than a pound of steel, and it's a rigidity problem. And really the only material that's like way more rigid than all these other basic building materials is carbon fiber. But even exotic materials like titanium and stuff have about the same rigidity for weight as wood. I mean, makes great airplanes.
Excuse to bring back
And the spruce goose.
Well, yeah, right. I hope.
Recyclable furniture.
Yeah, the comment was, so where are they going to get all the wood? But hopefully we're talking about small, relatively small amounts of wood.
Wooden space station would be interesting.
Those teak space stations require a lot of maintenance. Well, thank you very, very much. That was great.